The darkness doesn't feel empty. It moves quietly, rhythmically, like a deep tide you can sense more than see. Out here, far beyond the scatter of stars, far beyond the thin mist of galactic light, space bends in slow, patient curves. You can feel it before you understand it, the way a room changes when someone steps inside. Except here, the presence is enormous. Two of them, massive enough to pull the fabric of space-time into a trembling tension. You drift closer, not because you decide to, but because the landscape itself subtly guides you. Gravity is not a force here so much as a shape, an invisible valley carved into the universe. And at the center of that valley, two dark spheres circle each other with a grace that contradicts everything you know about violence and destruction. They move like dancers who have rehearsed for billions of years, tracing the same arc again and again, never tiring, never touching, not yet. The closer of the two is perhaps 20 or 30 times the mass of the Sun. Its event horizon spans roughly 180 kilometers across, about 112 miles, small enough to hide inside a single Earth-sized city, but dense enough to warp the world around it into a perfectly smooth sphere of shadow. Its partner is only slightly smaller, orbiting in a tight ellipse, the two locked by gravity in a bond far older than any human civilization. You don't see them the way you'd see a planet or star. What you see is the way they erase their surroundings. Light from the distant universe bends around their edges, pulled into rings and arcs that glow like distorted halos. Where light refuses to escape, there is only blackness, pure and absolute. But despite that darkness, the scene isn't silent. The vacuum vibrates, not with sound. Sound can't survive here, but with waves in space-time itself. Every orbit, every shift in the pair's motion sends ripples outward. You feel them as a slow stretching and compressing, a gentle rhythm passing through your body, altering the length of your outstretched hand by a distance smaller than the width of a proton before letting it return to normal, a cosmic heartbeat. These ripples spread in all directions, travelling for millions of light years. In a distant corner of a distant galaxy, one of these waves will one day wash through Earth, nudging two mirrors in a vacuum tube in a place called Washington State. Another pair in Louisiana, and a third in Italy. Those tiny nudges will be recorded as signals, a rising pitch, a sweep upward, a brief and delicate chirp, a ripple in space-time that began here, in this quiet orbiting dance. You watch the motion with a strange mixture of peace and unease. Peace because the dance is smooth, balanced, governed by laws older than stars. Unease because you know what lies ahead. These two black holes are losing energy, not in light, not in heat, but in these very waves. Every ripple that rushes outward steals a fragment of the orbit's momentum. Over thousands, millions, even billions of years, the pair spirals inward. The dance floor shrinks. Right now, though, they move slowly, gracefully. They might be circling each other once every few minutes, or every few hours, or, if you were farther out, even every few days. Time stretches strangely in the space around them, dilated by their gravity. If you had a clock, it wouldn't agree with one carried by someone far away. Even your heartbeat feels out of phase with the rest of the cosmos. But the motion continues. Two dark spheres sliding along invisible tracks carved by Einstein's equations, pulling one another forward, tugging the surrounding space-time into beautiful, swirling distortions. Behind each black hole, a faint lensing arc glows, stretched thin like a ribbon of starlight. You drift closer still, and the warping becomes more dramatic. Stars behind them appear to fracture into slivers. Light bends around their silhouettes in tight circles called Einstein rings. The fabric of the universe behaves like a lens. No glass, just geometry. In the warped reflections along the horizons, you catch fragmented images of worlds and galaxies that have nothing to do with this system. The black holes are mirrors of the cosmos, but mirrors that return nothing of themselves. But what's most striking is the stability of it. the quiet understanding that this is not rare or exceptional. Most black holes, contrary to the popular imagination, are not lone wanderers drifting through the dark. The universe is built from pairs and groups. Stars are born in clusters, and many form in binaries. When two massive stars live together, they also die together. Their cores collapse. Their outer layers explode into supernova remnants, and if the surviving cores are heavy enough, black holes remain, bound by gravity, bound by shared history, bound by the momentum of their former starlight. Some pairs come from an entirely different path, scattered into a mutual orbit inside a dense star cluster, or hurled together near a galactic center where interactions are almost chaotic. But regardless of origin, the result is the same: two black holes circling one another in a slow, shrinking dance. You hover in the warped space between them. The gravitational pull here is strong, but it doesn't drag you in. Instead, it feels like floating inside a valley of smooth curves, the ground sloping inward from every direction. The geometry around you tilts. Straight lines become impossible. If you threw something, a speck of dust, a grain of rock, it wouldn't fly away. It would trace a strange looping path, curving toward one black hole, then toward the other, switching allegiance as if undecided. A distant ripple passes through you again. Stretch, compress, stretch. The timing matches their orbit. You begin to anticipate it, the same way you anticipate waves on a quiet shore. Far ahead, beyond the orbit, the light of their host galaxy hangs like a faint smudge. Billions of stars, glowing and unaware, drifting slowly around a central supermassive black hole that governs the galaxy's inner dynamics. And here, on the outskirts of one of its spiral arms, two smaller black holes are performing an ancient gravitational ritual. If you could freeze this moment, suspend the pair exactly as they are, you'd capture a perfect portrait of curved space-time. But the universe never freezes. Their orbit shrinks by an immeasurably tiny amount with every revolution. To you, it's invisible. To the fabric of the universe, it's the beginning of something extraordinary. Eventually, millions of years from now, the dance will end in a collision so powerful it outshines every star in the galaxy combined. Not in visible light, but in gravitational waves. A burst of energy that shakes the cosmos. But right now, they are simply orbiting. Quiet, patient, balanced, two dark spheres moving in the gentlest rage the universe can offer. And as you drift in the warped stillness, you begin to sense that this is not chaos, not violence, not destruction. It is choreography, an invisible dance written in geometry, performed in darkness, and broadcast across the universe for any civilization advanced enough to listen. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it keeps these journeys alive. The darkness around you settles into something more structured, as if the shapes you saw in the dance begin revealing the rules behind them. To understand the orbiting giants you drift beside, you have to peel back the layers of what a black hole actually is, not the shorthand image that movies show, not a cosmic vacuum cleaner, not a hole in the fabric of reality, but an object defined with precision, an object predicted before anyone had seen one. The story begins in 1915 to 1916, when Albert Einstein published his general theory of relativity. Instead of imagining gravity as a force tugging between objects, Einstein described it as geometry. Mass and energy curve space-time, and everything else follows those curves. The theory was elegant, strange, and unsettling. It predicted bending starlight, shifting orbits, and distortions in time itself. But something even stranger emerged when the field equations were handed to a mathematician and physicist named Carl Schwarzschild. Schwarzschild was serving on the Eastern Front during World War I, writing equations in the trenches, literally. Despite the conditions, he sent Einstein a solution to the equations describing the gravitational field around a perfectly spherical, non-rotating mass. It was exact, the first of its kind, but inside that solution lurked a boundary unlike anything physicists had imagined, a radius where space-time seemed to behave catastrophically. Today we call it the Schwarzschild radius. For any object, you can compute this value based on its mass. Compress the object until all its mass fits within that radius, and gravity becomes so intense that not even light can escape. For the Sun, that radius is about 3 kilometers, roughly 1.9 miles. For Earth, it's about 9 millimeters, roughly 3/8 of an inch. No one imagined compressing a planet to the size of a marble, but mathematically the idea was clear. Cross that boundary, and the escape velocity exceeds the speed of light. Einstein himself initially suspected the idea was a mathematical oddity, a strange feature of the equations rather than a real object the universe would bother creating. Even Schwarzschild, who died shortly after publishing the solution, never claimed such objects actually existed. They were curiosities, artifacts, nothing more. But nature had other plans. When you watch the orbiting black holes ahead, the boundary you see, the clean, perfect sphere of darkness, is the event horizon. That's the physical manifestation of the Schwarzschild radius, the surface where outward motion becomes impossible. Light travelling outward falls inward instead. Lines of cause and effect get bent so far that all paths lead deeper. No signals come back out. It's not a physical surface like metal or rock. If you drifted across it, you wouldn't feel a thing. No bump, no threshold. But the universe would quietly seal your fate. The event horizon is a one-way door. You can enter, but nothing, not even information, escapes. A little closer to the truth lies the singularity, the point, or region, where the equations of relativity break down completely. According to classical theory, gravity becomes infinite. Density becomes infinite. The curvature of space-time becomes infinite. But infinities in physics aren't answers, they're placeholders. They mean the real theory, quantum gravity, hasn't been written yet. Whatever the singularity is, it's not a literal point you could see, it's a place where our understanding ends. And if the black hole is spinning, and most are, the structure becomes even stranger. The space around a rotating black hole drags inward on everything nearby, a twisting of space-time called frame dragging. This effect creates a region outside the event horizon known as the ergosphere, an oblate, bulging zone where nothing can remain stationary because space-time itself is being pulled around like a whirlpool. If you hovered there, even at full power, space-time would carry you along. Stranger still, energy can be extracted from this region. In 1969, physicist Roger Penrose proposed a way to steal rotational energy from a spinning black hole by splitting particles inside the ergosphere. Later, researchers realized similar processes can power the enormous jets streaming from galaxies, jets that travel thousands of light years. Some of the brightest structures in the universe may be fueled by the rotational energy of black holes tapped from the ergosphere. But to truly understand the black holes dancing in front of you, you have to think about scale. They come in at least 3 major categories: stellar mass black holes. These form when massive stars collapse after running out of nuclear fuel. A star with perhaps 20 to 100 times the mass of the Sun reaches the end of its life in a core collapse supernova. If the remaining core is heavy enough, typically above about 3 solar masses, it collapses into a black hole. Most stellar black holes range from 5 to 20 solar masses, though in low metallicity regions, where stars lose less mass through winds, they can form in the 30 to 60 solar mass range. The ones you see before you belong to this category. Their dimensions are surprisingly small considering their mass, tens of kilometers across, maybe the size of a city, yet weighing more than a star. Intermediate mass black holes. These are the mysterious middle children of the black hole family. Ranging from a few hundred to a few thousand solar masses, they're hard to detect. They don't shine like quasars, and they're too large to form from a single collapsing star. Some may form from runaway collisions in dense star clusters, others from repeated mergers of stellar black holes. A few candidates have been spotted, but the category remains one of astrophysics' biggest mysteries. Supermassive black holes. These giants sit at the centres of galaxies and weigh millions to billions of times the mass of the Sun. The Milky Way's central black hole, Sagittarius A, is about 4 million solar masses with a radius of around 12 million kilometres, roughly 7.5 million miles. Some galaxies host monsters with tens of billions of solar masses, enclosing event horizons larger than the orbit of Neptune. These massive objects didn't form from a single star. They grew through accretion, galactic mergers, and possibly the collapse of massive gas clouds in the early universe. When two such galaxies merge, their central black holes can form a binary spiraling together over hundreds of millions of years. But whether stellar or supermassive, black holes rarely live alone. And this brings you to one of the subtler truths of astrophysics. Binary systems are not the exception. They are the norm. Stars are born in clusters. Gas clouds collapse under gravity, fragmenting into many cores that form stars together. Among massive stars, the ones destined to become black holes, binary and triple systems are incredibly common. Observations show that the most massive stars form in binaries more often than not. Their orbits evolve as they age, sometimes tightening as the stars expand and shed mass, sometimes widening, sometimes becoming unstable. But when each star eventually collapses into a black hole, the pair often remains bound. A stellar binary naturally becomes a black hole binary if both stars survive long enough to collapse. If one star explodes asymmetrically during its supernova, it can kick itself out of the system, breaking the pair. But many times the kicks cancel out or are too weak to separate them. The result, two black holes born from the same ancestral cloud circling each other for millions or billions of years. That's the classical channel, but there are others. In dense star clusters, globular clusters, nuclear star clusters, the crowded cores of young stellar nurseries, close encounters are common. Black holes are heavy, and heavy objects sink toward the centre of clusters through a process called mass segregation. There, like dancers swapping partners, black holes can capture each other in gravitational interactions. A lone black hole passing near a tight binary can kick out one of the stars and take its place. Repeated encounters can form tight black hole pairs with eccentric orbits, sometimes merging quickly. Near supermassive black holes, the environment becomes even more chaotic. Gravitational torques, disk interactions, and high-speed stellar encounters create a kind of gravitational marketplace, constantly trading and recombining orbits. Black holes can pair up simply because everything else has been thrown out. The universe, in other words, is constantly setting up these dances. When you look again at the two orbiting shadows in front of you, you see the result of billions of years of astrophysical evolution. Everything from nuclear fusion to supernova explosions, stellar winds to gravitational interactions, density waves to chaotic scattering, all of it has conspired to place these two objects here, locked together. A black hole may be defined by a radius, by an event horizon, by the mathematical curve of space-time around it. But a binary black hole, two of them together, reveals the deeper truth. Gravity is a storyteller. Not a force, not a mystical pull, but a narrative written in motion, tracing every past interaction. Each orbit is a page, each ripple in space-time is a sentence, and somewhere in the distant future, instruments built by humans, tiny creatures from a small rocky planet, will read those sentences and begin decoding what happened here. Your view of the pair sharpens. The details of their horizons, their lensing arcs, their geometry, all of it becomes clearer when you understand the structure behind them. The darkness is no longer just an absence. It's a boundary with rules, history, and consequences. You're no longer drifting beside two mysterious shadows. You're drifting beside two solutions to Einstein's equations. living, evolving, merging in slow motion. And the dance you're witnessing is possible only because black holes are more than voids. They are objects with mass, with spin, with history, with origins rooted in the life cycles of stars. That is what a black hole actually is. You float in the warped stillness between the two orbiting black holes, watching their movement settle into a predictable rhythm. But behind this moment, behind these two dark spheres circling in quiet inevitability, lies a longer story. A story that begins not in darkness, but in light. Every black hole begins as a star, and not just any star, but one massive enough to burn furiously, live quickly, and die catastrophically. To understand how a pair like this forms, you have to follow that life cycle from the beginning. Two brilliant blue giants born together, burning through their fuel in parallel fates. It starts in a giant molecular cloud. Cold hydrogen and helium mixed with dust, stretching for dozens of light years. Regions of higher density collapse under their own gravity, fragmenting into multiple star-forming cores. These cores rarely create just one star. Instead, fragmentation produces clumps that become stellar siblings. For the most massive stars, the ones destined to become black holes, being born in a binary or higher order system is more common than being born alone. Imagine two stellar embryos forming side by side, separated by a few astronomical units, perhaps the distance between Earth and Jupiter. As they ignite nuclear fusion, they shine as brilliant O-type or B-type stars. Their cores begin burning hydrogen into helium at temperatures of tens of millions of degrees. Their surfaces glow blue-white, and their winds blast outward with enough force to carve cavities in the surrounding nebula. But they don't evolve independently. Binary stars share angular momentum. They interact gravitationally. They exchange mass. This early relationship profoundly shapes their eventual fate as black holes. The more massive of the two, the primary, evolves faster. It exhausts its hydrogen sooner, expands into a supergiant, and may transfer mass to its companion. These mass transfer episodes can dramatically change the future. The originally smaller star may grow more massive, while the original giant may lose enough material to alter its collapse. These exchanges complicate the story, but they also tighten the orbit. Angular momentum is redistributed, and the pair spirals inward. Metallicity plays a crucial role here. In astrophysics, metals refer to all elements heavier than helium. A star with low metallicity, common in early cosmic eras or in dwarf galaxies, loses less mass through stellar winds. That means it retains more of its original bulk and angular momentum. When it collapses, it forms a heavier black hole. This is why LIGO has detected mergers involving 30 to 60 solar mass black holes. Many of them likely formed in low metallicity environments where winds didn't strip away their mass. As the primary star nears the end of its life, fusion in its core produces heavier elements, carbon, oxygen, silicon, and eventually iron. When iron accumulates, fusion stops generating energy, and the star loses the battle against gravity. The core collapses in a fraction of a second. Temperatures soar to billions of degrees. Electrons and protons fuse into neutrons. The collapsing interior rebounds against the dense neutron core, sending a shock wave outward. If the shock is strong enough, the star explodes as a supernova, ejecting outer layers into space at tens of thousands of kilometers per second, tens of thousands of miles per second. The core collapses into a neutron star, or, if massive enough, into a black hole. For a binary, this explosion is a dangerous moment. A supernova can unbind the system completely. If too much mass is lost, or if the explosion is asymmetric, the newborn black hole can receive a kick that flings it away at hundreds of kilometers per second. But sometimes, often enough, the system survives. The orbit may widen or become more eccentric, but the two objects remain gravitationally tied. Then the companion star evolves, repeating the same process. After millions of years of burning bright, it too collapses and explodes. When the dust clears, the binary contains not two stars, but two black holes. This is the classic isolated binary evolution channel, the simplest story of how two black holes form together, but the universe rarely restricts itself to simple stories. Another path begins not in relative isolation, but in crowded environments like globular clusters. These are dense, ancient spheres of stars, hundreds of thousands packed into regions only a few dozen light years across. In such places, stars and compact remnants frequently pass close enough to perturb one another's orbits. Black holes, being the heaviest objects, sink toward the cluster's centre through mass segregation. There, in the crowded core, interactions become common. A black hole may encounter a binary star system, disrupting it. Sometimes the star is ejected and the black hole captures the remaining member. In other interactions, three-body encounters eject the least massive object, leaving behind a pair of black holes. These dynamical encounters can form black hole binaries with very tight orbits. They can also pump eccentricity, making the orbits elongated rather than circular. Most black holes in the classical channel circularize before merging, losing their initial eccentricity through gravitational wave emission. But a dynamically formed binary can retain its eccentricity all the way to the final inspiral. This leads to a gravitational wave signature distinct from the smooth chirp of ordinary mergers. There is another setting where dynamical formation flourishes, galactic nuclei. Near supermassive black holes, the gravitational environment becomes extreme. Objects accelerate to thousands of kilometers per second. Stellar mass black holes fall inward over time, collecting in a dense cluster near the galactic center. In such an environment, interactions are even more violent than in globular clusters. A single object can be involved in multiple three-body encounters within a million years. Pairs can form temporarily, break apart, and reform with different partners. A binary can lose energy to passing stars, shrinking its orbit. Or it can be perturbed into the path of the central supermassive black hole and be shredded by tidal forces. But when a stable binary does form, it often has a very small separation and very large total mass, ideal conditions for a merger detectable across billions of light years. There is a more exotic channel as well, one tied to accretion disks around supermassive black holes. In these disks, material gradually spirals inward, heated to extreme temperatures. Embedded within the disk, stellar mass black holes may become trapped in regions of high density, migration traps, where torques push them together rather than apart. Over millions of years, multiple compact objects can accumulate in these traps, forming binaries that eventually merge. Simulations suggest that repeated mergers in these environments could create black holes of 100 solar masses or more, providing one explanation for the upper mass range seen in gravitational wave catalogues. Each formation channel leaves its own fingerprints on the resulting binary, its mass ratio, eccentricity, spin alignment, and orbital separation. Isolated binaries tend to produce pairs with spins aligned with the original stellar rotation. Dynamically assembled pairs show random spin orientations. Migration traps often produce heavy masses and moderate alignment, while galactic nuclei favour high eccentricities. But how do we detect black hole binaries before they merge? They emit no light. Their horizons swallow everything. Yet indirect signatures exist. In X-ray binaries, a black hole can feed on a companion star, pulling material in through an accretion disk. These systems shine brilliantly in X-rays, but once the companion star is gone, once the second black hole forms, the pair becomes invisible in electromagnetic light. Still, the orbit may leave subtle clues. In rare cases, a binary black hole may perturb the motion of nearby stars or gas clouds. This is easier for supermassive binaries. Astronomers have found quasars with periodic variability, which may be signs of two supermassive black holes orbiting each other and modulating the accretion flow. Radio jets that precess like slow cosmic sprinklers may also indicate a binary at the heart of a galaxy. For stellar binaries, direct electromagnetic detection is nearly impossible once both objects have become black holes. They are too small, too dark, too quiet. Instead, astronomers rely on gravitational waves, the whispering signatures produced by their orbit. But these waves are extremely weak when the orbit is wide. Two stellar mass black holes separated by millions of kilometers, millions of miles, produce waves far below the sensitivity of LIGO or Virgo. Instead, researchers use population models to infer their existence. By studying the mass distributions of stars, their metallicities, binary fractions, and supernova kick velocities, astrophysicists can estimate how many binary black holes should exist in a given galaxy. The predictions suggest millions of such binaries in the Milky Way alone, most of them invisible until their final seconds. The two black holes you're watching now have lived through all of this. They were once stars, burning and shedding mass. They exchanged material, tightened their orbit, exploded, collapsed, stabilized. They survived kicks, shocks, and interactions. They persisted in a universe filled with chaos. Their current calm belies the furious processes that shaped them. You look at them differently now. Their orbit isn't just a motion, it's a memory, a fossil record of every force, every collision, every episode of mass transfer, every violent collapse that brought them together. The path from star to black hole is brief in cosmic terms, but the path from black hole formation to black hole merger is long. These two objects, once brilliant blue stars, shining a million times brighter than the sun, are now silent, cold, dark, yet still connected. Their dance is not an accident. It is the outcome of physics acting across billions of years. You drift in the curved space-time near their orbit, watching ripples cross your vision. Gentle gravitational waves that tell the story of their approach. And as you watch, you realize that binary black holes are not rare cosmic oddities. They are the natural, inevitable children of a universe that loves to build in pairs. The orbit of the two black holes seems steady, almost tranquil. But that stability is an illusion. If you watch long enough, far longer than a human lifetime, you would see the circle tighten, a slow, relentless drift inward. Not because of friction, not because anything is pushing or pulling on them, but because with every orbit something leaves the system. Energy. Not in light, not in heat, but in the form of ripples in space-time. Gravitational waves. To understand how two massive dark objects can lose energy to the very fabric they orbit within, you have to imagine space-time not as a static stage, but as something elastic. When an object moves, it dents that fabric. When two objects move rapidly around each other, those dents change position, and a changing dent sends out ripples, disturbances that propagate outward at the speed of light. A binary black hole, whether it's the small stellar kind or a pair of supermassive giants, is essentially a cosmic flywheel feeding energy into the universe. Albert Einstein predicted this in 1916, shortly after completing general relativity. At the time, the idea was abstract. He argued that accelerating masses should change the curvature of spacetime in a way that travels outward like a wave. These waves would stretch and compress space itself, but Einstein also believed they would be far too weak to measure. Detecting gravitational waves seemed as impossible as measuring the motion of atoms with a yardstick. Even among physicists there was doubt. Some wondered whether gravitational waves were real at all, or merely mathematical quirks in the equations. Over the next decades, the concept remained mostly theoretical. Beautiful, elegant, but unproven. Then came 1974. Two astronomers, Russell Hulse and Joseph Taylor, were studying a binary pulsar, a spinning neutron star emitting beams of radio waves orbiting another neutron star. This system, PSRB 1913+16, became one of the most precise laboratories in astrophysics. Every pulse arrived with exquisite regularity, like the tick of a perfect cosmic clock. But over time, the pulses began arriving slightly sooner than expected. The orbit was shrinking. The two neutron stars were spiraling inward at just the rate predicted by Einstein's equations. Not faster, not slower, exactly right. There was no other explanation. They were losing energy by emitting gravitational waves. It was the first indirect proof that gravitational waves exist. In 1993, Coulson Taylor received the Nobel Prize in Physics for this work. The discovery transformed gravitational waves from a theoretical curiosity into a real physical phenomenon, one that could shape orbits over millions of years. And if neutron stars could do this, then black holes, far more massive, should do the same. You look at the binary black holes in front of you with this in mind. Every orbit sends gravitational waves outward. The waves carry energy, and as that energy leaves, the orbit must compensate. It shrinks, slowly at first. In the early stages, the black holes might orbit each other every few days, losing energy so gradually that it would take 100 million years to notice a significant change. Imagine two black holes, each 30 times the mass of the Sun. At a wide separation, they lose energy at a rate roughly equivalent to a household light bulb, pathetically tiny for objects of such mass. But as the orbit contracts, the effect intensifies dramatically. The power radiated as gravitational waves depends steeply on the orbital radius. Smaller separations produce vastly higher emission. What begins as the power of a light bulb eventually becomes the power output of entire stars, then entire galaxies. And in the final moments before merger, gravitational wave emission can briefly exceed the luminosity of all the stars in the observable universe combined. It sounds absurd. How can two objects with no light produce more power than every star put together? The trick is that gravitational waves don't radiate electromagnetic energy. They radiate curvature, and for a fraction of a second, the bending of spacetime becomes so violent that the energy output is staggering. But long before that spectacular finale, the decay is slow, measured across cosmic time, not human time. For a typical stellar mass binary, the timeline might look like this. After formation, the orbit might be several million kilometers, several million miles across. The orbital period is perhaps a few hours to a few days. Gravitational waves at this stage are far too weak for us to detect. Over 10 million years, the orbital separation shrinks by a tiny amount, barely noticeable even with precise instruments. Over 100 million years, the binary tightens enough that the orbital period may shrink from hours to minutes. The gravitational wave signal begins to rise in frequency and strength. Over 1 billion years, the black holes approach the final inspiral. Each orbit now emits enough gravitational wave energy to dwarf the Sun's total power output. The long spiral is not linear, it accelerates. Each step inward speeds up the next. The closer they get, the faster they lose energy. The universe has many slow processes: radioactive decay, stellar evolution, the cooling of white dwarfs, but the inspiral of a binary black hole is among the most deceptive, almost imperceptibly slow for millions of years, then explosively fast at the end. But to appreciate the decay, you have to understand what exactly is being radiated away. Energy in general relativity isn't like energy in classical mechanics. You can't point to a spot on space-time and say, the energy is here. Instead, gravitational waves carry energy in a distributed, geometric way. They change distances, stretching space in one direction and squeezing it in another. If a gravitational wave passed through Earth right now at a detectable amplitude, distances might change by a fraction as tiny as 1 part in 10 to the 21st power. For comparison, if you stretched the 4-kilometer length of a LIGO arm by that amount, the change would be just 1,000th the width of a proton. Yet, LIGO can measure this. It can detect space-time shifting by a dimension humanity cannot meaningfully visualize. And out here, watching the orbiting black holes, you're seeing the source of such distortions before they have diminished across billions of light years. The waves passing through you are soft, gentle, like a distant tide. They deform nothing large enough for you to notice. But closer in, nearer the binary, the waves are stronger. If the Earth were somehow placed here, instruments would saturate instantly. The distortion would be far larger than anything LIGO was built to detect. The energy radiated from a typical 30 solar mass binary when the separation is still wide, say a few hundred kilometers, might be around 10 to the 22nd watts. That's 10,000 trillion watts. And remarkably, this is still the quiet phase. For comparison, the Sun outputs about 4 times 10 to the 26th watts. A galaxy like the Milky Way outputs around 10 to the power of 37 watts. A flashlight outputs maybe 1 watt, but as the black holes draw closer, gravitational wave power skyrockets. At separations of a few tens of kilometers, the power can reach 10 to the 49th power watts or more, roughly 1 trillion times the luminosity of all stars in the observable universe combined. But again, this occurs only in the final fraction of a second, just before the merger. The long spiral leading to that moment is where the real cosmic patience lies, and the timeline depends strongly on the masses involved. A binary of 2 10 solar mass black holes may orbit for billions of years before merging. 2 100 solar mass black holes may merge within a few hundred million years. Supermassive black holes, millions to billions of solar masses, may take hundreds of millions to billions of years to spiral inward through galactic cores. The physics is the same, the scale is different. The long spiral also depends on how the binary formed. Isolated binaries, those born from 2 massive stars, tend to start with smaller separations after the supernovae. Dynamically assembled binaries in globular clusters or galactic nuclei often begin with large separations and high eccentricities. In those cases, the orbital decay may accelerate significantly when the pair passes closest to each other in their elongated orbits. Think of it like 2 skaters orbiting one another while holding hands. If their orbit becomes more elliptical, they swing close together at high speed, losing a burst of energy during each pass. Over time, these bursts accumulate, shrinking the orbit rapidly. No matter the channel, no matter the history, the eventual spiral inward is inevitable as long as the binary remains bound. The universe doesn't allow perfect stability, not when gravitational waves are involved. You can see hints of this process by watching the orbit now. The black holes move in a clean, circular path, but the path is not permanent. If you could superimpose their orbits across millions of years, you would see a long, tightening coil. Each loop slightly smaller, each revolution slightly faster. And this decay is not special to black holes. Any orbiting masses radiate gravitational waves. The Earth and Moon emit them, shrinking Earth's orbit by a fraction of a millimeter every year. Every planet around the Sun emits gravitational waves, losing energy so slowly that it will take longer than the age of the universe to make a measurable difference. But black holes and neutron stars are far better at it. Their immense masses and tight orbits amplify the effect. The pair in front of you may merge in another 100 million years. For now, the loss of energy is gentle, invisible, almost tender. But the long spiral is underway, and nothing, not even the empty vacuum around them, can stop it. You feel another ripple pass through you. A gentle stretch, a gentle squeeze. A reminder that this universe is dynamic, restless, always radiating the stories of its own motion. You drift with that awareness, realizing that even in perfect darkness, no orbit is ever truly stable. The spiral has begun. The orbits tighten until the dance you've been watching, slow, vast, patient, begins to warp into something different. Everything accelerates. Distances shrink. Time seems to vibrate. You can feel the shift even before the geometry around you makes it obvious. The long spiral has brought the black holes into their final act. What was once an orbit measured in hours compresses into minutes, then into seconds. Each revolution becomes a blur of motion, like two shadows circling each other at nearly half the speed of light. Their horizons, smooth, dark, perfect spheres, begin to distort, not from any physical contact, but from the extreme warping of space-time itself. You're witnessing the last dozen orbits. After millions or billions of years of slow approach, the end arrives in a rush. As the black holes close in, they approach a boundary with a deceptively calm name, the innermost stable circular orbit, or ISCO. In the language of general relativity, this is the point at which circular motion stops being stable. Inside this radius, no orbit can persist. Anything that crosses it, light, matter, even a black hole companion, must plunge inward. It is the gravitational cliff, the last solid footing before the plunge. For a non-spinning black hole, the ISCO sits at 3 times the Schwarzschild radius, but if the black hole spins, frame dragging shifts it. Frame dragging is the twisting of space-time itself, pulled around by a rotating mass. Near a spinning black hole, space-time doesn't simply curve, it swirls. Imagine stirring thick honey with a spoon. The honey near the spoon moves with it. That's frame dragging. But here, the honey is space-time, and the spoon is a rotating black hole tens of kilometers, tens of miles across. The effect is so strong that within the ergosphere, the region outside the event horizon, nothing can remain still. Even light must rotate. Frame dragging changes the ISCO dramatically. If a black hole spins in the same direction as the orbit, the ISCO moves inward, allowing tighter orbits. If it spins opposite the orbit, the ISCO moves outward. Spin alignment becomes important here and tells astrophysicists about how the binary formed. Isolated binaries often have aligned spins. Dynamically assembled binaries tend to have misaligned spins or even spins pointed in random directions. As the pair approaches the ISCO, tidal forces surge. Tidal effects near black holes aren't like those near planets. They're not gentle pulls creating ocean tides. They're extreme gradients in space-time curvature, differences so sharp that the side of an object closer to the black hole experiences vastly different gravitational influence than the far side. If a star approached this close, it would be torn apart. If a planet came here, it would be shredded into vapor. Even a neutron star would be ripped to quarks. But a black hole is different. Its event horizon has no surface, nothing to tear. It simply continues moving along the path space-time dictates. The tidal forces distort the surrounding curvature, pulling the horizons into brief, shifting ellipses. For the first time, the black holes look less like perfect spheres and more like dark droplets stretching toward one another. This is the moment where numerical relativity, computer simulations solving Einstein's equations at full strength, becomes essential. Analytical formulas break down. The gravitational field is too turbulent, too nonlinear, too dynamic for simple approximations. Researchers with the Simulating Extreme Spacetimes (SXS) project have spent decades developing methods to simulate these final orbits. The results are astonishing. Their visualizations show the horizons deforming like fluid surfaces. The space between the black holes becomes a twisting valley where light orbits in chaotic, looping paths. Photon rings flare, stretch, and break apart as the curvature deepens. These simulations reveal something else as well. The final dozen orbits produce gravitational waves with a stunningly regular pattern. Each orbit sends a pulse outward, higher in frequency and stronger in amplitude than the one before. The gravitational wave signal climbs like a rising musical note, sweeping upward into what physicists call a chirp. But standing here, floating in space-time, you don't experience it as a sound. You feel it, a rapid stretching and squeezing, barely noticeable at first, then intensifying. It's as if the universe is tightening a drumhead beneath you. Each pulse is sharp, clean, rhythmic. The two black holes now orbit each other dozens of times per second. Their velocities approach a significant fraction of the speed of light. their horizons brighten, not in visible light, but in the sense that they lens the background universe more intensely. Distorted images of galaxies stretch into arcs. Photon orbits become more chaotic. The silence of space grows tense. Then comes the plunge. The plunge is not a collision in the conventional sense. Black holes do not smash or crack or break. Instead, they move past the ISCO and lose the ability to maintain a stable orbit. The curvature of spacetime funnels them inward. There is no more circling, only a final spiral so steep that it resolves into an inward plunge lasting only milliseconds. In this moment, the horizons distort dramatically. Each black hole pulls on the other's shape, creating a shared bulge of warped space-time between them. Numerical relativity simulations show the horizons stretching into a teardrop shape just before merging. The gravitational wave signal peaks here, a burst of emission so powerful that in this brief instant, the system becomes the brightest gravitational wave source in the universe. For a fraction of a second, the power radiated exceeds the output of all stars in 1 trillion galaxies combined. Then the horizons touch. It doesn't look like contact. There is no flash, no debris, no explosion. Instead, you see two shadows become one. The horizons merge like drops of dark liquid coalescing on a perfectly smooth surface. The surface tension here is geometry. The merging happens smoothly, mathematically inevitable, the only allowed outcome of curved space-time pushed to its limits. The exact moment of merger is almost impossible to perceive because it is not a localized event. It is a change in the topology of space-time. Two regions that once had separate, no-escape boundaries now share a single one. The merged horizon is wildly distorted, elliptical, bulging, rippling like a liquid bell struck by a mallet. These ripples aren't metaphorical, they're oscillations in the geometry itself. The new black hole rings, not with sound, but with gravitational waves, radiating away its shape imperfections. This ringing, the ringdown, is the start of the next chapter. But in the final minutes before merger, all the universe's attention is on the inspiral, the last orbits, the final dance, the rapid tightening spiral that ends in a single, smooth plunge. You watch the merged horizon settle, breathing in the strange stillness after the violence. The chirping waves fade, the distortion smooths, the new horizon begins to relax into its final form. It is over. Millions or billions of years of orbital decay, all converging into a finale that lasted less than a heartbeat, and in the quiet aftermath, space-time itself seems to exhale. The moment arrives with a kind of cosmic inevitability. Everything that has happened, the stars that lived and died to create these black holes, the millions of years of faint gravitational murmurs, the slow tightening of the orbit, the last frantic spiral, now converges into a single instant, a moment so brief it barely exists, yet so powerful it reshapes space-time across the universe. The two black holes reach the point of no return. Their orbits have accelerated to the point where they are circling each other dozens, then hundreds of times per second. Their horizons stretch and distort, pulled into elongated shapes by each other's gravity. Their combined curvature is so extreme that the universe around them behaves like a lens dipped in water, bending background starlight into flickering halos and chaotic arcs. And then, quietly, almost tenderly, their horizons touch, not with a crash, not with an explosion, but with the smooth, seamless joining of geometry. Event horizons do not collide like objects, they merge like concepts. The boundary that once separated two regions of no escape fuses into a single distorted surface. From the outside, it looks like two drops of pure darkness coalescing, forming a new shape that quivers violently against the strain of its own curvature. Inside, the singularities, if singularities exist as classical theory imagines, plunge toward each other and fuse. But whatever occurs beyond the event horizon is hidden forever from the universe. only the exterior geometry speaks, and it speaks in the form of gravitational waves. In these final milliseconds, the power output is beyond comprehension. A typical binary of two 30 solar mass black holes will convert around 3 solar masses worth of energy directly into gravitational waves, not over millions of years, not over hours, but in a fraction of a second. Using Einstein's famous relationship between mass and energy, that means 3 solar masses, approximately 5 times 10 to the 47th joules, released in approximately 0.2 seconds. That corresponds to a power output of roughly 10 to the power of 49 watts. Nothing else in the universe radiates with such intensity. Not supernovae, not quasars, not gamma-ray bursts. For a short instant, this black hole merger outshines the entire observable universe. Not in visible light, but in space-time itself. The curvature around the merging horizons becomes violent. Space stretches and compresses at rates that defy intuition. If you could hover impossibly close without being torn apart, you'd witness a storm of geometry, whirlpools of distorted space-time, rippling photon orbits spiraling outward, and arcs of lensed light blurring into continuous rings. Numerical relativity simulations, like those of the SXS project, show the horizons rippling like a struck drumhead, each oscillation radiating gravitational waves. The new merged horizon is not smooth. It is wrinkled, vibrating, full of imperfections carved into it by the dynamics of the merger. These distortions must be shed, and the black hole sheds them in the only way space-time knows, by ringing. This ringing is not a metaphor. It is a literal oscillation of the event horizon, described by quasi-normal modes. And those oscillations decay quickly, within milliseconds, emitting gravitational waves that fade away like the dying tone of a bell. But to reach the ringdown, the merger must first produce its signature, the chirp. Gravitational waves are often described as a chirp because the frequency rises as the orbit tightens. Imagine two masses orbiting one another. As they spiral inward, their orbital period shortens. Faster orbit means faster oscillation of curvature. Faster oscillation means higher frequency gravitational waves. So, as the black holes approach the final plunge, the wave frequency rises smoothly, low, higher, higher, until it reaches a sharp peak at the moment of merger. Then, suddenly, the signal stops rising. It transitions into the ringdown, a rapidly damped oscillation. This shape, this upward sweep, is the chirp. LIGO was built to detect precisely this signature. But when engineers and scientists designed the observatory in the 1990s and early 2000s, the sensitivity required bordered on absurd. To detect the passing of a gravitational wave, LIGO needed to measure changes in length smaller than 1/10,000th the width of a proton. Two 4-kilometer-long laser arms in Hanford, Washington and Livingston, Louisiana, each a vacuum so perfect it rivals outer space, were designed to act as rulers. Laser beams bounced back and forth inside them, forming interference patterns that would shift slightly when space-time stretched or compressed. For years, LIGO detected nothing but noise, seismic vibrations, thermal fluctuations, passing trucks, distant storms. It wasn't until the instrument upgrades in 2015, the transformation into advanced LIGO, that sensitivity increased enough to reach the theoretical threshold. And then, on September 14, 2015, at 5:51 a.m. local time in Louisiana, it happened. A short signal, a rising chirp lasting just 0.2 seconds, one that matched precisely the predictions of numerical relativity. The source was later determined to be a binary black hole merger, two black holes, 36 and 29 solar masses, merging into one of 62 solar masses, with the remaining mass radiated away in gravitational waves. The event was named GW 150914, year, month, day, to the thousands of scientists distributed across the LIGO and Virgo collaborations. The discovery was first met with disbelief. Could such a clean signal be real? Could it truly match the simulations so perfectly? Teams independently analysed the data, tested for glitches, checked for instrument noise artifacts, and searched for any signs of human interference. Nothing. The signal was pure. When the announcement finally came on February 11th, 2016, the scientific world erupted. It wasn't just the discovery of gravitational waves, it was the first direct detection of a black hole merger. The first proof that stellar mass black hole binaries existed. The first demonstration that spacetime could be measured on subatomic scales. The first confirmation that Einstein's most exotic predictions were correct in the strongest gravitational fields ever tested. The global reaction ranged from astonishment to awe. Newspapers called it Einstein's triumph. Physicists called it a new era of astronomy. Some compared it to the moment Galileo first pointed a telescope at the sky, because for the first time humanity wasn't just observing the universe through light, it was feeling the universe move. Standing here, watching your own binary black holes merge, you understand what those scientists sensed on that September morning. The chirp isn't just a curve on a graph, it's the encoded history of motion. The final syllable of a story written across millions of years of gravitational inspiration. The event horizons finish merging. The new black hole ripples and settles. The violent curvature fades into smoothness. The gravitational wave emission declines rapidly, leaving only the faint decaying ringdown. The universe is calm again. What remains is a single, larger black hole. Quieter, darker, but carrying the memory of everything that happened. Its spin reflects the angular momentum of the original binary. Its mass reflects the energy lost to the waves. Its geometry reflects the final equilibrium of space-time. And as you drift in the stillness, you realize something profound. This moment, the merger, wasn't destruction. It was transformation. Two horizons became one. Two histories became one. Two solutions to Einstein's equations became one. The universe took two massive objects and wrote them into a single line of space-time. What you witnessed was not chaos, not violence, but the smoothest, most elegant joining the cosmos can produce, a moment where space-time itself sang. The violence of the merger fades almost instantly, as if someone has lowered the volume on the universe itself. What remains is a single, misshapen black hole, still trembling from the force of its own creation. Its event horizon ripples, bulges, and recoils in complicated patterns. These distortions are not random. They follow a strict mathematical choreography, written by the geometry of space-time. This phase is called the ringdown. If the merger was the climax, the ringdown is the resonance that follows, the cosmic equivalent of a bell struck so hard it nearly shatters, then gradually settling back into silence. But the ringing here isn't sound, it's curvature. Gravity itself oscillates. The newly formed black hole begins as a wildly deformed object. Its horizon looks like a dark droplet pulled in different directions, wobbling with the imprint of the final plunge. Within milliseconds, these distortions radiate away through gravitational waves. But the shape doesn't smooth out all at once. Instead, it transitions through a set of oscillation patterns known as quasi-normal modes. These modes are the allowed vibrations of a black hole's geometry, solutions to Einstein's equations that describe how a perturbed horizon relaxes to equilibrium. Each mode has its own frequency and damping time. But unlike the clean tones of a musical instrument, these vibrations decay extremely rapidly. They're quasi-normal because they aren't sustained. They exist just long enough to tell the universe that a new black hole has been born. Think of the event horizon as a membrane, though it isn't a physical surface, being stretched into an odd shape and then let go. The membrane snaps back, overshoots, snaps again, and radiates its distortions outward as gravitational waves. With each oscillation, the amplitude shrinks. The black hole calms. These oscillations encode deep information, the final mass, the final spin, and whether general relativity holds true under the most extreme conditions imaginable. A black hole in general relativity is astonishingly simple. It can be fully described by just two numbers, mass and spin. Charge is theoretically possible, but astrophysical black holes cannot retain significant charge in real environments. This simplicity, called the no-hair theorem, means that once the ringdown is over, all memory of the merger's chaotic details has vanished. Only the final mass and spin remain as physical quantities. But for the short time during the ringdown, the frequencies of the quasi-normal modes allow physicists to measure both of these values directly. It works like this. Each quasi-normal mode oscillates at a frequency determined solely by the mass and spin of the black hole. Measure that frequency, infer the mass and spin. Measure a second mode, check consistency. If the inferred numbers disagree, something is wrong with general relativity. That is why the ringdown is so powerful. It is a direct test of Einstein's theory in the strongest gravity ever observed. You watch the newborn black hole quiver and settle into shape. The oscillations, though imperceptible to your eyes, are written in the gravitational waves passing through you. The frequency is higher than during the inspiral, but the amplitude falls sharply. The chirp stops, replaced with a rapidly fading hum, a gravitational sigh. During the inspiral and merger, the binary acted like a dramatic tension coil. All the complexity of orbital dynamics, mutual frame dragging, non-linear curvature effects, everything tangled together. But once the ringdown begins, the system becomes much simpler. The new horizon absorbs the last distortions, the curvature stabilizes, the geometry becomes Kerr-like, a rotating black hole in its final state. If the original binary had two black holes of 30 and 30 solar masses, the remnant might be around 55 to 58 solar masses, depending on how much mass was radiated during the merger. If they began with spins aligned with the orbit, the final black hole might spin at around 0.7 of the maximum possible rotation rate allowed by relativity. If the spins were misaligned or if the merger was eccentric, the final spin might differ significantly. These details, mass, spin, kick velocity, are the fingerprints of the cosmic birth event. Not all mergers create perfectly centered black holes. In fact, many receive a gravitational recoil or kick from asymmetric wave emission. If the waves radiate more power in one direction, the black hole is pushed in the opposite direction, sometimes at hundreds of kilometers per second, even thousands. Some black holes may be flung out of their host galaxies entirely, but regardless of where it travels, every newborn black hole sings the same song, a ringdown that encodes its shape and future. As the oscillations fade, the gravitational wave signal decays exponentially. The amplitude diminishes until the waves become indistinguishable from the background hum of the universe. In LIGO's data, this part of the signal lasts only a handful of milliseconds, barely enough to extract one or two modes. But even those few modes were enough to change physics. After GW 150914, the first detection, physicists immediately began analysing the ringdown portion of the data. Though the signal-to-noise ratio was low, the frequency matched perfectly with the predictions for a roughly 62 solar mass black hole spinning at about 0.67 of its maximum. This was the first direct observation of a black hole transitioning into equilibrium, a black hole in the act of becoming itself. Later detections revealed clearer ringdowns. Events such as GW 170729 and GW 190521 produced high-mass black holes with louder post-merger signals, making the quasi-normal modes easier to identify. And as the network expanded, from LIGO in the United States to Virgo in Italy and Kagra in Japan, triangulating ringdowns became more precise. Recent studies using LIGO Virgo Kagra have pushed the frontier even further. Physicists have searched for multiple quasi-normal modes in a single event to test the no-hair theorem, compared the inferred mass and spin from the inspiral with those from the ringdown, looked for deviations in the decay rates that might hint at new physics, tested exotic alternatives to black holes like Grava stars and boson stars, which predict different oscillation patterns. used Bayesian analyses to place tight limits on violations of general relativity. So far, the universe has remained loyal to Einstein. General relativity has passed every ringdown test, but the sensitivity of current detectors allows only a glimpse. Third-generation observatories, like the Einstein Telescope in Europe or Cosmic Explorer in the United States, will capture ringdowns with dramatically higher precision. They might detect dozens of oscillation modes. They might measure black hole properties to within fractions of a percent. They may reveal tiny discrepancies that point toward quantum gravity, string theory, or new fundamental fields. But for now, the ringdown you're witnessing is a pristine example of what relativity predicts. A single horizon vibrating, a gravitational bell struck by the merger, a space-time waveform fading into silence. The oscillations continue for a moment longer, each one weaker, each one shorter, until the distortions vanish entirely. The black hole becomes perfectly smooth, a Kerr black hole defined solely by its mass and spin. Its future is simple. It will persist indefinitely, unless another merger, accretion disk, or passing star disturbs it. You drift in front of it, sensing its quiet. This is the universe's most efficient eraser. All details of the merger's chaos are gone. Only the final state remains. And in that stillness, you feel the profound symmetry of it all. A system that spent millions of years in motion has condensed its entire story into a short ringdown, an encoded whisper that spread across billions of light years, carrying the memory of a merger that no observer could ever see directly. The universe rarely gives clear signatures, but a black hole ringdown is unmistakable, precise, brief, final. It is the moment a new black hole is born, and the moment the last vibrations of its creation fade into the silence of space-time. The new black hole in front of you sits in silence, but it isn't an outlier. The universe is filled with black holes, thousands, millions, maybe billions of them, spread across galaxies like an invisible population we're only now beginning to count. And as soon as scientists had the tools to listen to gravitational waves, the picture of that population changed dramatically. For a long time, almost everything we knew about stellar black holes came from X-ray binaries in the Milky Way. These are systems where a black hole feeds on a companion star, pulling gas from its surface. That accreting gas heats up and emits X-rays, making the system bright enough to study. The masses measured from these systems fell into a narrow band. Most were around 8 to 15 times the mass of the Sun, with very few exceptions. It was easy to assume this was typical. That most black holes looked like this. That this was the universe's preferred recipe. But LIGO quickly showed that this was only a tiny slice of the story. The first detections revealed black holes far bigger than expected, 30 solar mass objects, 40 solar mass objects, even heavier ones. Nothing in the Milky Way's X-ray population prepared astronomers for that. It signaled that many black holes form in places very different from our own galaxy, places where stars evolve in a different way. The key difference is metallicity. In astrophysics, metallicity simply means the fraction of elements heavier than helium inside a star. High metallicity stars, like those in the Milky Way today, lose a huge amount of mass through stellar winds. Heavy elements make these winds stronger. As a result, these stars shed much of their outer layers before collapsing, leaving behind smaller black holes. Low metallicity stars behave differently. Their winds are weak, they keep their mass, and when they collapse, the core that remains is massive enough to form a black hole in the 30 to 50 solar mass range, or even higher. It's why LIGO's catalogue is full of mergers involving heavy black holes. These systems likely formed in primitive or early universe environments, small galaxies with little chemical complexity, or regions where ancient stars were still forming with very few metals. But heavy black holes aren't unlimited. Something stops them from reaching the upper ranges you might expect, and that boundary is created by a powerful process inside the most massive stars, pair-instability. Deep inside a star with a huge, hot core, energetic photons can convert into electron-positron pairs. That process removes pressure from the core and the star contracts. The temperature shoots up even higher, and instead of stabilizing, the star undergoes explosive burning. If the core is moderately large, this happens in pulses, giant eruptions that blow off enormous amounts of mass. Those stars can still form black holes, but the eruptions prevent them from becoming too large. If the core is extremely massive, the process becomes catastrophic. The entire star detonates in a single overwhelming explosion, a pair-instability supernova. And unlike other supernova, this one leaves no remnant at all, no neutron star, no black hole, everything is destroyed. This carves a clear gap into the mass spectrum, a region between roughly 60 and 120 solar masses where black holes cannot form from ordinary stellar collapse. This is the pair-instability mass gap, yet LIGO has detected candidates inside or near this gap. JUDEW 190521, for example, involved black holes around 85 and 66 solar masses. Hard to explain with normal stellar evolution. The most likely explanation is hierarchical mergers. Smaller black holes merging first, forming a larger one, which later merges again. These kinds of mergers require dense environments, globular clusters, nuclear star clusters, or disks around supermassive black holes, places where black holes can interact repeatedly. Gravitational encounters there can swap binary partners, tighten orbits, or bring older merger remnants into new pairs. In those regions, it's entirely possible for black holes to climb the mass ladder, step by step, into territory where normal stars cannot go. Beyond those heavy stellar black holes lies an even more mysterious class, intermediate mass black holes. These would weigh anywhere from a few hundred to a few thousand solar masses, too small to act like the supermassive monsters at galaxy centers, but too big to come from a single star. For decades, they were purely hypothetical. Astronomers searched for them in star clusters, in unusually bright X-ray sources, in dwarf galaxies, but the evidence was always ambiguous. Gravitational wave astronomy changed that. The remnant of GW 190521, with a mass around 142 solar masses, is widely considered the first clear intermediate mass black hole ever detected, and it likely didn't form from a lone star. It almost certainly formed from earlier mergers. It's a trace of something astrophysicists have long suspected, that intermediate mass black holes may grow inside clusters through repeated collisions of stars or black holes, eventually becoming seeds for supermassive black holes. Other hints have shown up in the electromagnetic spectrum too. Some ultraluminous X-ray sources shine far brighter than a stellar black hole should allow. A few of them may contain compact objects in the intermediate range. One especially strong candidate is HLX1, which may host an object around 20,000 solar masses. That number remains debated, but it shows how close the field is to confirming a population once thought nearly impossible to detect. As gravitational wave catalogues expand, astrophysicists are building detailed population models to understand how all these black holes fit together. They look at the mass distribution as a whole, studying how the low-mass population from 8 to 15 solar masses differs from heavier groups, how often binaries form in isolated star systems versus dense clusters, how metallicity affects black hole mass in different galaxies, how common hierarchical mergers are, whether spins tend to align or randomly scatter, how many black holes fall near the pair-instability gap? How much evidence exists for intermediate mass formation? These models combine observations with simulations of billions of stars evolving over cosmic time. Every piece of data from LIGO, Virgo, Kagra helps refine the picture, and each new event adds another dot to a growing cosmic map, one showing that black hole populations are far more varied than astronomers once believed. Even within the Milky Way, there may be tens of millions of stellar mass black holes wandering in the dark, most completely inactive. They don't accrete, they don't shine. They reveal themselves only when they disturb a companion star, or when they merge and send a ripple across spacetime. Out here, hovering near the quiet remnant of a merger, it's easy to forget that this single object is only one entry in a long, complex story about how black holes form, grow, and pair up across the universe. Some come from massive stars in metal-poor galaxies. Some are built through repeated collisions in crowded clusters. Some rise into forbidden mass ranges where stars cannot go, and some keep climbing towards the territory of intermediate mass black holes that were once only theoretical. These populations are not separate, they're connected in subtle, evolutionary ways, and the more gravitational wave detections accumulate, the clearer the structure becomes. A cosmic family tree traced not through light but through the shape of space-time itself. The black hole in front of you is stellar-sized, dozens of solar masses compact enough to cross in a heartbeat. But elsewhere in the universe, a very different kind of pair exists. Not tens of kilometers across, but millions. Not weighing as much as a star, but as much as an entire galaxy's core. These are supermassive black hole binaries, the giants formed when galaxies themselves collide. To understand how these pairs form, you have to zoom out, far beyond star clusters, beyond spiral arms, beyond individual galaxies, and think about the universe as a landscape built on mergers. Galaxies do not simply drift alone. They grow by devouring one another, drawn together by gravity, reshaped through slow cosmic encounters. When two galaxies begin falling toward each other, the process takes hundreds of millions of years. Their outer stars stretch into long tidal tails. Gas clouds crash and compress, igniting bursts of star formation. The structure of each galaxy becomes distorted, but deep at the centers, something even more important happens. Each galaxy's supermassive black hole sinks toward the gravitational middle of the newly forming system. This sinking isn't passive. It happens through a process called dynamical friction. Imagine a massive object moving through a crowd of smaller bodies. As it passes, it gravitationally attracts the nearby stars and dark matter particles, pulling them slightly forward. But because gravity creates an overdensity behind the object, the net effect is a drag force. The black hole loses momentum and spirals inward. Over time, both supermassive black holes, one from each original galaxy, sink toward the shared center of the merger. Once there, they begin orbiting one another. At first, the separation might be thousands of light years, then hundreds, then tens. Gradually, they form a bound pair. Two black holes millions or billions of times the mass of the Sun, locked together in a slow dance that can last far longer than any stellar binary. But once they reach separations of about a light year or less, something interesting and problematic happens. Their orbit stops shrinking efficiently. Stars that wander close enough to extract energy from the pair are gradually depleted. Gas flows may not penetrate deep enough to continue the drag, and gravitational waves at this distance are still too weak to take over. This is known as the final parsec problem, a long-standing question in astrophysics. How do supermassive black holes close the last light year of separation and actually merge? For years, simulations struggled to solve it. The binary would stall at roughly a parsec, about 3.26 light years, never reaching the inspiral where gravitational wave emission could finish the job. If this stalling were universal, the cosmos would be filled with supermassive binaries that never merge. But nature, as usual, found a workaround. More recent models suggest that galaxies are not smooth, uniform disks of stars. They are clumpy, asymmetric, turbulent, triaxial. All of this changes the gravitational environment. Instead of running out of stars that can exchange energy with the binary, the galactic core keeps feeding new ones into the loss cone. Gas inflows can stir the stars, redistribute angular momentum, and create torques that continue shrinking the orbit. Bars and spiral instabilities in the galactic core can funnel mass toward the center, deepening the gravitational well. Dense nuclear star clusters play a role too. The The complex interactions among thousands of stars create chaotic gravitational encounters that constantly refill the reservoir of orbits capable of extracting energy from the binary. And if the galaxy is gas-rich, viscous gas disks can form around the binary, interacting gravitationally and generating additional torque. Together, these effects push the supermassive black holes inward far enough for gravitational wave emission to take over. Once that happens, the last phase, like with stellar binaries, accelerates rapidly. But unlike stellar mergers, the gravitational waves from supermassive black holes have wavelengths so large, so long, that we cannot detect them with LIGO or Virgo. Their waves are measured by timing the signals of pulsars spread across the sky. These cosmic lighthouses emit regular radio pulses. If a supermassive binary sends out gravitational waves across the galaxy, the waves stretch and compress spacetime in a way that causes the pulses to arrive slightly earlier or later. Over years or decades, this tiny effect builds a telltale signature, a correlated pattern across multiple pulsars. This is the work of pulsar timing arrays, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, and others. After decades of monitoring, they announced evidence in 2023 for a gravitational wave background. This background is likely produced by thousands of supermassive binary black holes spread throughout the universe, each one contributing its own faint rumble to the low-frequency gravitational environment. These are not individual chirps like the stellar mass black hole mergers detected by LIGO. Instead, they form a cosmic bass note, deep, slow undulations in spacetime that take years to complete a single cycle. Though pulsar timing arrays hear the universe's low-frequency hum, electromagnetic astronomy has its own clues. Some quasars, the hyperbright centers of galaxies powered by accreting supermassive black holes, show periodic changes in luminosity. These variations sometimes occur on regular timescales, months, years, or decades. Several of these periodic quasars are strong candidates for harboring supermassive black hole binaries, with one black hole modulating the accretion flow of the other. Other hints come from radio jets. These powerful beams, launched by spinning black holes surrounded by magnetized disks, sometimes precess, slowly wobbling in a way that suggests the black hole itself is being torqued by a companion. This precession can leave a corkscrew imprint in the jet, visible in long baseline radio observations. If the jet's wobble matches the dynamics expected from a binary system, it's considered a strong signal. Some galaxies show double-peaked emission lines, possibly indicating two distinct gas disks orbiting separate black holes. Others contain two bright compact radio cores separated by only a few light-years. Individually, these clues are subtle, but taken together, they form a growing picture. Supermassive binaries are common. They are everywhere galaxies collide. They are shaping the cores of galaxies throughout cosmic history, and their influence is enormous. When two supermassive black holes orbit each other, they stir the surrounding gas and stars. They can heat the nuclear region of a galaxy, regulating star formation. They can carve cavities in gas disks, redirecting flows that alter how the galaxy grows. They can tilt or disrupt bars, warp galactic centers, and alter the dynamics of stars on tiny orbits. When they finally merge, the resulting black hole may receive a gravitational recoil, like smaller black holes do, but scaled up dramatically. Some recoils might reach thousands of kilometers per second. In extreme cases, the remnant black hole could be kicked completely out of its galaxy, leaving behind a star cluster that once orbited it. Observers have found compact star clusters with unusual velocity profiles that may be the fossil signatures of such ejected giants. On a larger scale, supermassive binary mergers help explain the relationship between galaxies and their central black holes. Galaxies with bigger bulges tend to host bigger black holes. This correlation likely emerges because the history of black hole growth through mergers and accretion is intimately tied to the galaxy's own evolutionary path. When galaxies grow, their black holes grow with them. When galaxies collide, their black holes eventually collide as well. As you drift near your own newly formed black hole, the much smaller stellar kind, it's strange to think that the universe contains versions of this event so large they reshape galaxies. Supermassive black hole binaries influence star formation, regulate gas in the galactic core, and even change the trajectory of galaxies after a merger. They also provide the deepest, slowest gravitational rhythms the cosmos produces. Stellar black hole mergers hum for fractions of a second. Supermassive mergers hum for years. And somewhere between those low, slow oscillations, pulsars pulse steadily, letting astronomers measure the faint distortions passing through the Milky Way. Each pulsar acts like a tiny metronome, tapped on by spacetime itself. Across the universe, in billions of galaxies, supermassive black hole binaries are moving toward each other, slowly spiraling inward. Most won't merge in the current age of the universe, but many will someday, and when they do, their final waves will ripple across the cosmos like the deep bass of a universe-sized instrument. You remain near your much smaller black hole, feeling the faint echoes of its recent ringdown. The calm horizon in front of you is one outcome of a long cosmic process, but in the centers of galaxies, the same process unfolds on unimaginably larger scales, guiding the evolution of stars, gas, and entire galaxies as they move through cosmic time. The quiet around the black hole feels almost absolute, but the universe is never truly silent. If your senses were tuned to the right frequencies, you'd notice a constant trembling in space-time, tiny ripples stretching and squeezing everything everywhere, all the time. Most are far too faint to feel. Some were born from events like the merger you just watched. Others come from neutron stars, white dwarfs, or collisions happening millions of light years away. For nearly a century, these waves were nothing more than a mathematical prediction. Einstein wrote about them in 1916 and immediately doubted they'd ever be detected. The distortions are unimaginably small, far smaller than anything you encounter in daily life. And yet, a few decades ago, scientists began building machines capable of measuring them. Those machines now form the backbone of gravitational wave astronomy. The most well-known instruments are LIGO, Virgo, and kagra. They're not telescopes in any traditional sense. They don't collect light. They don't take pictures. Instead, they measure distance, and how that distance changes when a gravitational wave passes through Earth. The changes they look for are tiny. A wave might stretch a 4-kilometre arm by far less than the width of a proton, then compress it by the same amount. Detecting that requires a level of precision that borders on the unbelievable. Each observatory uses the same basic principle: laser interferometry. A laser is split into two beams. One beam travels down one arm, the other travels down the second, each 4 kilometers long for LIGO and 3 kilometers for Virgo. At the end of each arm, the beam reflects off an ultra-polished mirror and returns to the central building. When the beams reunite, they interfere with one another. If both arms are exactly the same length, the interference pattern is stable. But if a gravitational wave passes, one arm becomes a little longer, the other a little shorter, and the interference pattern changes in a measurable way. That sounds simple. The reality is anything but. To make this work, the arms need to be some of the cleanest vacuum tubes ever created, longer than any tunnel you've walked through, but emptier than interplanetary space. Air molecules, dust, and even stray light would spoil the measurement. Every mirror has to be isolated from the Earth's constant shaking, and the Earth shakes a lot. Waves hitting coastlines, trucks on nearby roads, earthquakes on the other side of the world. All of these would normally overwhelm the signal, so the mirrors are hung on multi-stage pendulums. Each stage filters out part of the motion. At the bottom of these suspension systems are 40-kilogram mirrors made of fused silica, polished and coated with such care that imperfections are measured in atoms. Active control systems constantly monitor their positions and adjust for vibration. Virgo uses even more elaborate suspensions, super-attenuators with multiple stages of seismic filtering. Kagra goes further still. It's built underground in Japan, where the rock dampens surface vibrations, and its mirrors are cooled to cryogenic temperatures to reduce thermal noise. That makes Kagra the world's first cryogenic gravitational wave detector. Together, these observatories form a global network. When a gravitational wave reaches Earth, it hits one detector slightly before the others. By comparing those slight delays and the shape of the signal, scientists can locate the source on the sky. The network turns the planet into a giant listening array. But no matter how advanced these instruments are, they can only hear part of the gravitational wave universe. They're sensitive to frequencies from roughly tens of hertz to a few thousand hertz. That's ideal for stellar mass black holes and neutron stars. But if you drop below that range, into the millihertz or microhertz domain, the Earth itself becomes too noisy. Human activity, tides, seismic rumblings, all of it drowns out the signal. This is where the next major leap comes in. To hear lower frequencies, the detectors must leave the planet entirely. The Laser Interferometer Space Antenna, or LISA, will be the first large-scale gravitational wave observatory in space. It's a joint mission between ESA and NASA planned for the 2030s. Instead of two arms, LISA uses 3 spacecraft forming an enormous equilateral triangle, and instead of being 4 kilometers long, each arm is 2.5 million kilometers. That distance is so vast that a laser beam takes several seconds to cross just one arm. The spacecraft don't sit inside tubes. They float in orbit, separated by millions of kilometers of empty space. Each craft carries a freely falling test mass, a small object that moves only under gravity. The spacecraft uses tiny thrusters to stay centered around its test mass, shielding it from sunlight, dust, and everything else that might disturb it. Laser beams travel back and forth between the spacecraft, forming a gigantic interferometer that listens for gravitational waves with periods of minutes or hours. LISA is tuned to a very different part of the spectrum than LIGO and Virgo. It will pick up supermassive black hole binaries spiraling together over years, small objects orbiting gigantic black holes in near-perfect detail, white dwarf binaries inside our own galaxy, possible signals from the early universe, long before galaxies formed. Its view will be slow, deep, and broad, sensitive to the gentle, long wavelength waves that Earth-based detectors can never reach. But even LISA doesn't fill the entire spectrum. Between the frequencies of LISA and those of LIGO lies an important middle zone, the decahertz band, around 0.1 to 10 hertz. This is a quiet part of the gravitational wave sky, home to events that neither LIGO nor LISA can easily detect. Many binaries begin their inspirals here. Intermediate mass black holes may merge here. White dwarf systems evolve through this range on their way to tighter orbits. Several proposed missions hope to explore this gap. DeSigo and BDeSigo, planned by Japanese teams. ELGAR, a European concept using atom interferometry. AEDGE, another atom-based proposal. And other designs exploring kilometre-scale baselines in space. If even one of these missions becomes reality, gravitational wave astronomy will gain a new set of ears, able to track a single binary for months as it sweeps upward from the decahertz range into LIGO's range. That kind of long-term observation would let astronomers forecast mergers, alert telescopes in advance, and test general relativity across a wider span of frequencies than ever before. Taken together, all these instruments, on Earth and in space, form the beginning of a full gravitational wave spectrum, just like the electromagnetic spectrum. Each band reveals different structures, different physics, and different cosmic players. At the lowest frequencies, nanohertz, pulsar timing arrays trace the slow oscillations of supermassive black hole binaries spread across the universe. At millihertz, LISA will study mergers of galactic giants and compact binaries in our own galaxy. At decahertz, future missions will capture intermediate mass black holes and early inspirals. At tens to thousands of hertz, LIGO, Virgo and Kagra hear the final moments of stellar mass mergers. Together, they turn spacetime into a kind of cosmic instrument, an enormous vibrating field that carries information no telescope can provide. Standing here, near the quiet horizon of a stellar black hole, it's easy to forget how much of the universe is invisible to light. But gravitational wave astronomy has opened a new sense for humanity, and while the detectors are still young, their reach is expanding quickly. The next decades will be filled with new signals, new populations, new tests of physics that can only be done by listening to the shape of space-time itself. The black hole beside you has settled into calm equilibrium, but not every merger in the universe follows such a clean, quiet path. Some form in environments so chaotic, so crowded, or so unconventional that their orbits twist into strange shapes and their mergers unfold in ways far from the smooth spirals predicted for isolated binaries. These are the extreme and exotic scenarios, the ones that stretch astrophysics, challenge modelling, and push gravitational wave detectors into the edges of what they can observe. A good place to begin is with one of the most surprising mechanisms for forming tight black hole pairs, hierarchical triples. Many stars, and therefore many black holes, are born not in pairs, but in groups of 3 or more. If 2 objects orbit each other closely while a third orbits farther out, the gravitational effects of the outer companion can dramatically reshape the inner orbit over long periods of time. This process is known as kozai lidov oscillations, named after the astronomers who studied them in the 1960s. The idea sounds simple. The third body perturbs the inner binary's orbit. The outcome is anything but simple. Under the right conditions, the inner orbit becomes highly eccentric, stretched into a long, thin ellipse. Over thousands or millions of years, the eccentricity can grow to extreme values. At the highest excursions, the 2 inner black holes swing dangerously close on every pass, losing significant energy to gravitational waves during the near miss. Eventually, those repeated bursts of emission shrink the orbit enough that a merger becomes inevitable. This channel produces black hole mergers that look very different from the slow circular inspirals most people picture. Instead of a gradual tightening, you get a series of fast, close approaches, each one throwing off a flash of energy until the final plunge happens almost suddenly. Some gravitational wave events detected by LIGO and Virgo may already hint at this. A few signals show mild eccentricity in their earliest detectable cycles. Eccentricity tends to vanish quickly as gravitational waves circularize the late inspiral, so catching even a trace suggests the system may have evolved through a channel like this. Hierarchical triples also tend to produce misaligned spins, since the third body can tilt the inner orbit in complex ways. Another environment full of exotic possibilities is a dense stellar cluster. Imagine a region with hundreds of thousands of stars packed into a volume only a few dozen light-years across. Globular clusters, nuclear star clusters, and the cores of young massive clusters all fall into this category. In these places, black holes do not sit quietly. They interact constantly, scattering each other, swapping binary partners, forming new pairs, and breaking apart old ones. In a cluster, black holes naturally sink toward the center through mass segregation. The heaviest objects drift inward first. Over time, the core becomes dominated by these massive remnants. There, 3-body encounters become common. A black hole passing near a binary may eject one member and replace it, forming a new binary almost instantly. Other encounters harden existing binaries, tightening them until gravitational wave emission takes over. But clusters also enable something even more exotic: repeated mergers. If a black hole remains in the cluster after merging, it can merge again. And again. Every time, it becomes heavier. After multiple cycles, a black hole that started with, say, 20 solar masses could grow to 80, 100 or more, creeping toward or even beyond the pair-instability mass gap. Events like GW 1905-21 may be the result of exactly this process. The presence of very massive black holes in gravitational wave data is one of the strongest hints that dense environments are contributing significantly to the population. These repeated mergers leave signatures. For one, the resulting black holes often have high spins because each merger transfers angular momentum to the remnant. They also tend to have random spin orientations because dynamical encounters scatter objects in every direction, and their mass distribution may show gaps and bumps created by the hierarchical buildup. Some clusters may even produce intermediate mass black holes through this slow stair-step growth. If enough mergers occur before the black hole is ejected by gravitational recoil, an object in the range of a few hundred or a few thousand solar masses may form. But the most exotic possibility is older than any star or cluster: primordial black holes. These hypothetical objects would have formed not from collapsing stars, but from density fluctuations in the early universe, tiny overdensities squeezed so tightly during cosmic inflation that they collapsed directly into black holes within fractions of a second after the Big Bang. If they exist, primordial black holes would form a population unlike anything produced by stellar evolution. Their masses could range from tiny asteroid-sized objects up to tens of solar masses or more. Some theories suggest they could make up part of the dark matter. Others propose that the earliest black hole mergers detected by LIGO could be primordial in origin. There's no solid evidence yet, but the idea remains alive because early universe physics is still full of unknowns. A primordial binary would have formed in an entirely different way from stellar black hole binaries. They could start with extremely eccentric orbits, shaped by the small-scale gravitational landscape of the early universe. They might have no spin at all, or very random spins. Their mass distribution could differ from what stellar evolution predicts, and they might merge across cosmic time in ways that leave unusual fingerprints in gravitational wave data. So far, the evidence is neutral. Some merger events look compatible with primordial black hole origins. Others look more like products of stellar or cluster evolution. Upcoming detectors, especially ones sensitive to lower frequencies, may finally distinguish between these scenarios. Numerical relativity adds another dimension to the exotic cases. When the orbits aren't circular, the merger becomes far more complex. Highly eccentric binaries, those that formed through close encounters or triple interactions, produce gravitational wave signals with bursts rather than smooth chirps. Instead of a steady rise in frequency, the waveform contains sharp spikes during each close approach. In extreme cases, two black holes can undergo a series of rapid slingshot-like passes before the final plunge, emitting wave packets that challenge standard detection algorithms. Simulations show that eccentric mergers can produce distinctive gravitational wave harmonics, extra layers of structure beyond the dominant mode. These higher-order modes contain information about the object's masses, spins, and orbital configuration. Detecting them would let astrophysicists map the exact shape of the merger, almost like rebuilding the orbit from the ripples it left behind. Higher order modes are difficult to detect with current sensitivities, but hints have appeared in a few gravitational wave events. They tend to be more prominent when the binary has unequal masses or a high degree of eccentricity. As detectors improve, these modes will become a key tool for diagnosing exotic formation channels. They may also reveal something deeper: small deviations from general relativity. If the ringdown contains unexpected frequencies, or if the merger emits harmonics not predicted by Einstein's equations, that could point toward new physics or exotic compact objects. So far, every event fits relativity's predictions closely, but the exotic scenarios offer the best chance to see something new. Another frontier lies in black holes embedded in accretion disks around supermassive black holes. In those environments, gas can shepherd stellar black holes into migration traps, regions where torques from the disk cancel out, causing many objects to accumulate in the same orbit. There, repeated interactions can create tight binaries, induce eccentricity, and even trigger mergers directly inside the disk. These mergers occur in the presence of gas, meaning they may produce electromagnetic signals alongside gravitational waves, something that has long been considered unlikely for black hole mergers. A candidate for such a multi-messenger merger was reported in 2020, a flare from a quasar called J1249 plus 3449, which brightened shortly after a gravitational wave event. The association remains uncertain, but it hints at a path for future detections. And then there is the possibility, still speculative, that black holes might interact with hypothetical ultralight particles or dark matter fields. If these fields exist, they could form clouds around spinning black holes through a process called superradiance, subtly altering the black hole's spin or the frequencies of its ringdown modes. Detecting such deviations would require exceptionally precise gravitational wave measurements, but the exotic scenarios are where such phenomena would be most visible. All of these processes, triples, cluster dynamics, primordial black holes, disk-induced mergers, eccentric inspirals, higher-order modes, expand the landscape far beyond the standard binary evolution story. They reveal how gravity behaves when multiple massive objects share the same environment. They also show how much variety exists in the universe's merger population, far beyond the smooth, circular inspirals first imagined when gravitational wave astronomy was young. Near the quiet remnant beside you, the spacetime feels calm again. But out across the universe, in star clusters, galactic centers, and the early cosmic dawn, black holes are approaching each other on far stranger trajectories. Some neat, some chaotic, some shaped by forces we barely understand. And as each one moves toward its final plunge, it leaves clues in the waves that radiate outward, waiting for detectors on Earth and in space to catch them. From a quiet distance, the black hole in front of you feels almost like an afterthought, one remnant in a universe built from countless such moments. But as you drift in the stillness, it's hard not to sense the larger pattern. Everywhere across the cosmos, gravity is arranging its steps, stars move, galaxies merge, and black holes come together in motion so slow they stretch across millions of years. And yet, when they finally meet, the universe trembles. It's strange to think that a merger, something so silent and invisible to human senses, can leave ripples that sweep across everything. Earth spins through those ripples without noticing. The oceans don't lift, the air doesn't move. But deep inside, laser interferometers, frozen test masses, shift by impossibly small amounts, and humanity learns that somewhere, two invisible giants completed their orbit. For most of history, no one imagined we'd ever be able to listen to space-time itself. We watched the sky, we built telescopes, we measured light, but gravitational waves opened a channel that had been silent for billions of years. Suddenly, we're hearing what the universe has been doing all along. Binary black holes aren't just oddities, they're architects of the cosmos. They shape the centers of galaxies, they heat star clusters, they sculpt the gravitational landscape even where no light shines. Every time two black holes merge, they write another line in the history of structure formation, transferring energy, momentum, and spin into the space around them. And when the waves from those mergers reach us, they carry information that couldn't have been discovered in any other way. A black hole's mass, its spin, the shape of its orbit, the environment it came from, all of that is encoded in the gentle stretching of space-time. Listening becomes a form of cosmic archaeology. As detectors grow more sensitive, the universe grows louder. Third-generation observatories will hear mergers from billions of light-years away. LISA will drift through the quiet landscapes of millihertz frequencies, following supermassive black holes as they circle each other for years. Pulsar timing arrays will keep tracking the deep gravitational hum of countless slowly orbiting giants across cosmic time. And even then, many questions will remain. How many black holes formed in clusters or triples or gas disks? How many were born in the first seconds after the Big Bang? How many are spiraling inward right now in galaxies too faint to ever see? Somewhere out in the vast dark, two black holes are beginning a slow drift toward one another. Their orbits are so wide that the first ripple won't reach Earth until long after our civilization has changed beyond recognition. But the motion has already started. The universe is always moving, always reshaping itself, always writing new rhythms into space-time. For now, you float near a quiet remnant, the airless calm around it almost meditative. A place where the violence has already passed, where the motion has settled, and where the geometry has smoothed back into silence. And in that silence there's a kind of wonder, knowing that even here, in the deepest calm, the universe is still dancing.